So as promised, we're on to meeting the neutrophil. This is number 39. Again, if you don't have the sheet, you can download it right near where the link is. There should be a link for the PDF for the, you can print the paper out. And let's see, let's start with showing you a real neutrophil. So there it is, he or she. Now I can say there she is or there he is. I might actually be able to tell. Because a neutrophil, look at this nucleus, it's got like 1, 2, 3, 4, 4.5 maybe different lobes. And so they're sometimes they actually use their name. They call them polys because poly means many lobed nucleus. They're famous for that. And sometimes in one of these lobes, maybe like here or something, in females, you can see their pair of X chromosomes, right? The X chromosomes are longer than the Y. So a boy has a short Y and a long X, and a girl has XX. And this thing will stick out as a little lobe, like maybe this thing right here sticking out. You'll see this little, they call it the drumstick, and you'll see a little thing sticking out there. So this is helpful, like, you know, sadly at crime scenes or something, if they find you know, blood, we need to identify, you know, who was it and what, you know, they could tell right away whether it's at least a male or female and have a clue who to, you know, anyways. So when just simply by the blood sample, you can probably tell. Not every cell has that drumstick sticking out, but enough of them that just by looking at somebody's blood, if you look at the neutrophils, you can tell whether it's male or female. So that's a little neat tidbit of a little trivia about the neutrophils. Okay, and you can see here that they're not so heavily granulated. They don't have the big dots. They're still kind of pinkish, but the granules, and like here where the artist showed it, they showed the granules as kind of white, kind of, they're not red and they're not blue. So, and there's this 1, 2, only has 3, right? And the little connectors, just like we saw in the eosinophil. So, but they still, as you can see, they stain kind of pinkish. So, in our real drawing, we are going to zoom in here. We're going to do the same thing. We're going to draw 2 versions of the cell. So we'll draw kind of a realistic one here. And we're going to draw a cartoony one here. So for a realistic one, we're going to have you can make it however big or blobby, we can have them go wherever you want to. It does not have to look like mine. And we're going to make some, I want to make them kind of pink. You know how it's kind of an overall pinkish color? Well, I'm going to make it kind of some of the vesicles sort of like just very light pinky. They're not really red like the eosinophil, but it's kind of pink. And the vesicles don't stain red or blue, but are neutral. And that's where it gets its name, neutral, neutrophil. It loves neutral, doesn't like anything better, doesn't like blue or red. So it's kind of like pinkish. I know pink is kind of like red, but anyways, it's fairly neutral. Okay, and same thing, you're still kind of like 10 to 12 microns big. You can see in these pictures, right, the cells that are around them in all of these pictures, right, these are the erythrocytes, the red cells. So they're a little bit bigger than the red cells. Okay, for our cartoon, this guy's going to look really, really weird. We're going to make the nucleus have 3 lobes, but we'll make it like this. One of these lobes will make it into the mouth, and the other ones will kind of make into their eyes. How's that? It looks like some kind of goofy thing from outer space or something. And then up here, well, let's do this first. Let's give them the kind of pink freckles, very light pink. Now, doesn't necessarily mean it's a girl. Maybe it might be. If you want to make your cell a girl, you can like put an extra little bump coming off one of them or something if you want to. Okay, so there's some pinkish freckles. We have to make freckles because it's a granulocyte, right? So it has these granules. So we do need to have them showing up in our cartoon. And then we're going to put, oddly enough, a red cross on its forehead. Now, everybody knows when there's an emergency, there's an accident, whatever's happening, the vehicles that show up, or the organizations that show up, often have this symbol on them. This is kind of like for first aid, right? Your first responders. So this is supposed to remind you of first responders, ambulances, fire crew, emergency workers, people that can deal with the situation right away, first thing. So this reminds you that the neutrophil is a first responder. It's your body's first responder. I mean, you put in parentheses, ambulance, Red Cross, stuff like that. People that are there right away on the scene helping out. So, one last thing. The hair for this guy, what we're going to do is little tiny things like this. These are little squares or whatever. And these are going to be little protein receptors because it has a special job. If it's going to be first on the scene and it's going to on the scene of infection and you've got pathogens, nasty things leaking in, you got to remember, this is a cartoon, right? These cells don't really have eyes. They can't see. How do they know what's around them? They have to sense it with receptors because they can't actually see. So these are receptors for all kinds of pathogens. Pathogen meaning bacteria, virus, protozoa, little nasties that get in your body. Okay, and then another thing you need to know about them will be in this note. The open mouth reminds us that they eat by phagocytosis. Remember, phago means eat and cyto is cell. So these are actually, the macrophages are the big eaters. Some people call these the microphages, the little eaters. So these things can eat the pathogens. They come along and they see a virus or bacteria, they gobble it up. These guys can eat maybe about only like a handful of them before they die. They don't live very long. So let's review the information over here. Our body makes about 100 billion of these per day. That's a lot. And we have 5 times as many neutrophils in reserve, like in our bone marrow, as we do in circulation. So these guys, there's some floating in your blood all the time, but when necessary, when they run into something and they start signaling, what, we need more of us, aren't enough, your body can release a whole flood of them very quickly. And some of them sit, I think, in the spleen too, and you can get quickly released. Okay, so they float in blood until they're needed in tissues. When they get the chemical signals that they are needed, they leave the vessels by squeezing through the cracks between endothelial cells. And remember, we think we saw this already. The cell can squeeze through, if this is a capillary, the cell can just squeeze right through and get out. In fact, I think we're going to draw that picture next. Let's go down here and we're going to draw it down here in just a second. Let's just mention lifespan is just a few days, so you're replacing them all the time, even if they're not needed. You know, they just, if you don't get an infection or anything, you know, some of them you won't need. They dissolve and get recycled. And note here that pus, like that nasty kind of whitish stuff when you get a little infected toe or something, is mostly dead neutrophils. All those guys go there, they do their job in a couple of days, and they die. And why is pus white? Because it's white cells, white blood cells. Okay, let's go down here in this section and see how they get from the blood into the tissues. So I'm going to draw right here a little strip of blood vessel and then some body cells down here. So at the top we're going to draw, I think we had this in the clotting drawing, these endothelial cells. Remember, endothelial cells are just a special kind of epithelial cells, but when they line the capillaries they're called endothelial. And then down here, about halfway down, we'll make another one around here. And then maybe just leave a little gap right here for our little cell guy to get through. And then down here we're going to make some body cells. And you can make them kind of cartoons. I'm going to put some eyes. These are going to be very alarmed body cells. They're a little bit scared. Here. Here. Because a pathogen has gotten into the tissue. So we'll put right here, let's put some little bacteria. Remember, bacteria are small in comparison to body cells, maybe even smaller than that. These are very big pathogens. So these cells see them. Oh no! Ah. And of course, cells can't really talk. How do they send out the alarm? This guy over here, he doesn't know what's going on yet. He's just sitting here. This guy sort of gets what's going on. So what happens is they send chemical messages. We'll put some dots for the little messages. They release help, help, SOS messages that go up to these endothelial cells. And the endothelial cells, with their little eyes, look down and go, oh, okay, we'll go call some neutrals for you. So the neutrophils, we'll just put an N there, are cruising through the bloodstream. And all of a sudden, these endothelial cells, what do? How are they going to stop the neutrophil? You know, they could like call out, hey, come down here. Send a little chemical message. But how's the neutrophil actually going to stop? This blood is, your heart's just pumping it through. And it doesn't have, you know, how's it going to stop? It's going to keep right on flowing. So these endothelial cells actually put out little hooks, little protein gadgets. Remember, like there's so many cool protein gadgets in the body. And one of them is little hooks. And the neutrophil actually has kind of got, look like Velcro hooks or something. Now these of course are not to scale. You wouldn't be able to see them. I'm making them really big. So the neutrophil has kind of matching little hooks. And when it comes down and it bumps down to here, it'll start catching. Okay, this one's already come down on these little hooks, and they'll slow it down and stop it right here. And then it can squeeze through. Because these things can kind of move like an amoeba. It's kind of weird, but you don't think of your body cells as being little kind of amoeba things, but they can. And it'll squeeze through the crack. And it even has a chemical. It can make a chemical that will dissolve the desmosomes, the little joints, right, that hold the cells together, the little junctions. It can dissolve those junctions and make the crack bigger and slide through. And then, of course, once it's through, and into here, we'll put it down here now. There's a little end down here. Once it's through, then these endothelial cells will patch together real quickly. They'll start making new junctions and fix themselves. So the neutrophil gets down into this space, and this space has a special name. You can go down and you can highlight it down here. It is called the interstitial space. That's the space between the body cells. Now sometimes the cells are pretty tight. Now I've really drawn them far apart here for, exaggerated. Maybe they have dendrosomes or some kind of junctions, and sometimes they're really, really tight, right? Some are super tight junctions. These guys kind of have loose ones. But this, even if they're a lot tighter, there would be some kind of space that the neutrophil could slide through. And so it slithers through, and remember, it can even dissolve these if it needs to get through. It's like, excuse me, I need to cut your ties for a minute. Get down here, slither, and it's going to go after the bacteria. And it has sensors on it that can smell, sort of, the bacteria. So bacteria, they're stinky. They're putting out all kinds of, chemicals too. They don't realize if they smell, right? And so it will go closer and closer. It's like playing hot and cold. Am I getting warmer? Am I getting warmer? And the closer they get, the stronger the chemical senses get, until they get right there, and then boom, they'll go and they'll just eat it up, swallow it. Okay, so we cover all this down here. I think so. All right, so that is how these guys are. I'm gonna label that. Remember, these are called endothelial cells, and these are chemicals, and these kind of communication chemicals are often called cytokines or cytokines. We'll see quite a number of them playing an important role in future drawings. Okay, so the neutrophil can get into the tissues and gobble up the bacteria. So what happens once it swallows the bacteria? Wow, now we have a bacteria inside. Okay, so it's got to have some way to kill it once it gets in. It's like, eating a live goldfish. That's kind of gross, but you have digestive juices, it'll get rid of it. So the bacteria, the neutrophil, it has lysosomes, right? Those little digesting vacuoles it could grind away at. But these guys you need to get rid of them fast, right? They're dangerous. Viruses, bacteria, you got to get rid of them real quickly. So what's going to happen is they are going to use chemical weapons. Really nasty stuff, harsh stuff. So let us draw the pathogen. So when the neutrophil swallows the pathogen, in this case we're going to draw a cute little bacteria, it ends up in a little vesicle, because that's how endocytosis works. You take the thing in, you pinch off, and the little thing is then inside a little vesicle. So here's our vesicle, and here's our little pathogen, cartoony as he may be. Okay, and he thinks this is kind of nice right now. There's his little flagella, and let's say he might be even just laying on his back, enjoying the comfort. This is kind of nice here because he's got a cozy little space. This isn't too bad. Being inside a neutrophil is not too bad. And maybe he'd be like, oh, he's not maybe too worried about the lysosomal chemicals. He maybe can just dissolve those. So he's not too upset right now. He's thinking, make a little thought bubble for him over here. He's thinking, what a cozy little room. But little does he know, it's not going to be cozy for very much longer. And this bubble now, this vesicle, is called a phagosome. Right, so that's an eating body, phagosome. Now, it's maybe not this big. I drew it kind of nice and big and roomy, but it maybe doesn't have that much extra space. But in our cartoon it does. So, unfortunately for the pathogen, there's going to be some chemicals dumped into this area. It's going to turn into a very nasty place very shortly. And one of them, I'll draw them as little bottles. And you, of course, know there are no bottles inside. Okay. another one. Let's draw a third one over here. You can draw the bottles wherever you want. They don't have to be in any special location. They don't have to be perfect. And they're dumping out into here. And then we need to draw something over here too. We need to draw, believe it or not, an oxygen tank. Have you ever seen those medical ones like scuba divers carry tanks? Just think of like scuba diving oxygen tank, right? And it kind of looks like that. And it has this little regulator thing on top. Just make a little squiggle. And then we'll hook it up to a hose here. And we're going to label it O2, oxygen. Okay, and I'm going to label my drawing inside a neutrophil, because we haven't drawn the whole neutrophil here, right? This is what's going on inside the cell. So this is just one tiny part of the cell. We haven't drawn the nucleus or anything here. So let's talk about the oxygen first. If you go down to number 1, you can see it says superoxide is an oxygen molecule O2 with an extra electron stuck on by a special enzyme. The electron goes flying off like a bullet. So let's, right in this space here, draw what the superoxide molecule looks like. It's got 2 oxygens, which is normal. Oxygen always hangs out in pairs. A singular oxygen, one O flying around by itself, is not good. That's not happy, because it's looking to pick up some more electrons. So each one of these guys, if you want to make the Lewis dot structure, they've got, each one of these guys contributes 6, and they share 1, 2, 3, 4, 5, 6, 7, 8. How do they draw that here? 1, 2. I guess they put it on the bottom. They tend to put these little dots on the bottom. So you put 2 on the side, 2 on the bottom, and they put 2 here. This is what you'll see if you look it up. That's what you'll see on the internet. And then they put a negative here. It's got an extra electron stuck on. So this is normal oxygen, and here's the extra electron. Okay, so it was happy as O2, but an enzyme comes along, and it's like loading the gun. It's like if you have a pop gun or something, and you push, or a spring-loaded gun, you stick that extra electron on there, and it'll stick for a little while. I'm just going to make mine red. I like to make electrons red. It'll stick there for a little while, but it's going to go flying off very soon, because it doesn't really belong there. And that's what happens. And the electron is sort of like the bullet. It goes flying off, and it'll hit, a lot of times what it'll do is it'll hit a, actually, if it hits the membrane, the phospholipid membrane, you know, it's got all these little phospholipid molecules. Okay, so each one of those looks like this. There's a carbon atom here, 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 right? So, and then there's a phosphorus, and there's a glycerol here, right? There's atoms inside here too. So what'll happen is it'll go up the chain. It'll hit here. These guys are all happy, and the electron will come flying in, and it will dislodge one of the electrons that's already happily here, and then it's going to have to go find a new home, and it goes maybe to the next guy. I'm going to stick here, and it kicks one out, and it's like a chain reaction of this loose electron trying to find a place. Well, when it finally sticks somewhere, it may not be the best place, and it may end up bending this molecule and making it the wrong shape, and then it can't do its job. And if you get enough of those, you know, one phospholipid being the wrong shape isn't really going to make that much difference in your life. But as you get older and the years roll on, you get more and more of this little tiny bit of damage going on. And then eventually some organs start to break down. So this is, as I wrote down here, superoxide is a very common, quote, free radical found in your body. It kills pathogens, but it can also damage your cells. So these are like the free radicals. Have you heard people talking about, you need to take vitamin E, you need to eat a lot of fruits and vegetables. They have natural antioxidants, and selenium's an antioxidant. So they're you don't really want these free radicals banging around your body, but the strange thing is that you do need them. They play a role in your body, and they fight disease. Your body makes these things. Your body makes free radicals, right? For a purpose, needs it. But too much of a good thing isn't good, so you get too many rolling around, and that's not so good. Okay, so we're going to label one of these bottles up here. This one's going to be H2O2. Now you might think, oh, H2O. I know that one. That's water. You're right. Well, here's H2O2. So if this guy wasn't here, and we moved this one over, we'd have water, H2O. Look at that. There's an extra oxygen in here. And this is called hydrogen peroxide. And you may have some of this at home, like in your first aid kit, or maybe you clean with it or something. That's often what it looks like. They come in brown bottles, usually. And what a lot of people use them for is you get a cut, some kind of a wound, you sterilize it, you pour the hydrogen peroxide over it, and it kills germs. It helps your cut stay clean. That's exactly what your body uses for it, to kill germs. But it does it inside these little phagosomes. So as I have down there, number 2, hydrogen peroxide, H2O2. Yes, the same stuff that is in your first aid kit for sterilizing wounds. The bullet here is the second oxygen molecule. So as we just commented, H2O, right? It's a perfectly good molecule. It's very happy. Water is a very stable, happy molecule. And this one's not quite so stable. So this oxygen is very likely to take off, and then this can move over to form water. And remember, a lone oxygen is not a happy camper, and it can go and do the same thing and kind of knock other molecules apart. So let's see, what are other little poisons here we're going to pour on top of the pathogen? We're going to pour something, we're going to say HOCl. So down here we have it listed as HOCl, a form of bleach. Yikers, it's a form of bleach, and this is called hypochlorous acid. Now, with the bleach that you put in your swimming pool or something, it's probably like NaClO, so it has sodium in it. It doesn't have sodium, but this is basically a type of bleach type molecule. Now, the same thing here, that O, because HCl, hydrochloric acid, is very happy, and there's an extra O jammed in there, and that O is going to leave and turn into a bullet. When the neutrophil is making a lot of this, your mucus turns green. The enzyme that makes this molecule, is kind of greenish in color. Here's another exception to the rule, like things are always clear. Well, this enzyme is kind of green. Green mucus suggests bacterial infection rather than viral. So they really step up the bleach for bacteria. Well, you probably bleach your countertops or something and get rid of bacteria. The cell does the same. So the doctor says, what color is your mucus? Well, if it's clear, that usually indicates more of a virus. But if it's green, that usually means there's bacteria involved. So we're also going to write in this last one, it has digestive enzymes. It can also tear apart the body. Once these things kill it, this can go in here and digest it and recycle all the parts, get it all chopped into bits. So it's got oxygen. They're all oxygen-based weapons. This one's superoxide, hydrogen peroxide, HOCl, which is basically bleach, and it's got enzymes to dump in there. And that guy is not going to look happy for much longer. He's going to not be around. But there's even more. We're going to note down here. Neutrophils can also suck iron, Fe, iron, out of bacteria. And the bacteria die without iron. This bacteria needs to have iron to do its respiration because it's a living thing. It needs oxygen. It needs to get energy. Well, in our bodies, we have the electron transport chain, all that stuff too, in mitochondria. Now, he doesn't have mitochondria, but he still has to do respiration, and it needs iron for respiration. And so if you take the iron out, then he can't get energy, and he dies. And just a little side note, your body really knows this well, and it can, if you've got a bacterial infection for a long time, you'll end up kind of short on iron. Your body will try to prevent the bacteria from multiplying, and your body will store, and put here, you want to add a note, body will take iron out of your blood and hide it from the bacteria. Isn't that crazy? So if you have a chronic infection for a long time, it's likely that they test your blood, you're going to say you're anemic, you don't have a lot of iron in your blood, but your body did that on purpose to try to hide the iron from the bacteria. So that's another little cool fact about the weapon that your body has to fight these guys. So next we're going to go on and talk about the macrophage.